Hey guys, welcome back to Pop 'em Up Chem. In this video, we're going to be continuing our odyssey into structure determination and introducing a new technique that's Proton NMR spectroscopy. We're going to have this video in two parts, and in this part, we're going to be looking at the theory and what a hydrogen environment is. Quick question based on the infrared spectroscopy we did last time. Pause the video and have a go at that. So hopefully you remember the three main factors at play were bond length, bond strength, and atomic mass of the atoms. So NMR stands for nuclear magnetic resonance, and this is a method that we can use to determine the structure of organic molecules. It helps us find the different environments of atoms that are in these molecules, and the output is in a graph form, these kind of spectra. In this example, this is a carbon-13 NMR, which we won't use, but it has a similar pattern where we see a peak and we see a certain shift. So the way this works is we dissolve the sample in a solvent and put it in a sample tube. And you'll see from the diagram here that that glass tube is surrounded by a series of wires which are themselves subjected to a magnetic field, in this case going from left to right. So we've got a magnetic field going through the sample, and then we've got wires that are carrying electromagnetic radiation into the sample, so they're going to effectively radiate the sample. And then we've got wires that have an electromagnetic radiation output, and it's that output that we will use to then form the spectra like we saw on the previous slide. It's important to recognize that the spectra aren't quite as simple as in infrared spectroscopy, and the signals have to undergo a complex processing technique called Fourier transformations, but luckily we don't have to do that. So, why H NMR? Or any NMR? In fact, what allows us to do NMR? Well, there's a specific property of atoms that allows us to do this called spin. Now, we won't go into too much detail about what this kind of spin actually means here, as that's a bit beyond the course of the IB, but basically any nuclei that has an odd mass number is suitable for NMR, as it's going to have what we call spin half. And this means that it's going to make it active inside that magnetic field that we looked at when we looked at the setup of our NMR. So common are carbon-13 and proton NMR H1, which is what we're going to focus on. So that means that some isotopes of elements will not be active. Carbon-12, for example, has an even number, and so only the carbon-13 isotope with the odd mass number is going to be active for NMR. The reason for this is when we have an unbalanced spin on a nuclei, that nuclei will change its orientation if we add energy when it's in the presence of an external magnetic field. Again, this interaction is slightly more complicated than I'm illustrating here, but this will do for IB purposes. So let's have a look at how all of this comes together. So in the method, we have a sample, and in that sample, we have all of the nuclei that are active have kind of properties similar to that of bar magnets. Now, these bar magnets can be oriented in any direction in the absence of a magnetic field, so we have this kind of random distribution. However, when we apply a magnetic field, these kind of mini bar magnets are going to rearrange themselves in one of two ways. They could align themselves with the field, so the field lines going in the same direction, or they might go against the field lines, so they may align themselves in the opposite direction. We call this either spin aligned or spin opposed. So it might look something like this. In this example, 3 of these are spin aligned and 2 are spin opposed. So now we can expose this sample to the electromagnetic radiation that was carried in by the wires that we looked at in our schematic diagram earlier, and this will make all of the nuclei flip to the opposed position, because the opposed position is a higher energy position because it obviously goes against the magnetic field. So as we put energy into the system, the nuclei that are currently aligned with the magnetic field will be flipped and will become spin opposed. This means that when these nuclei relax and move back to their spin aligned state, they will release that electromagnetic energy that has been absorbed, and that will be given out. And it's that radiation that's given out in that relaxation process that we will detect and then process. So it's all very well having these signals come out, but what are we actually measuring and what are we measuring against? That's why we need a reference. So a reference, just like we had in the infrared spectroscopy, is going to be something we're going to measure other compounds against. And the most common of these is called TMS, or tetramethylsilane, and it has a very symmetrical structure, as you can see here, silicon in the middle with 4 CH3 groups coming out of each side. So a small amount of TMS can be placed in the sample tube and run before we do another sample, and we use this signal as R0. And the reason we use TMS in particular is due to its physical property of having a very low boiling point, which means it's easy to clean, but also because of its chemical properties. If we look at the structure here, we can see it's very symmetrical and there's lots of carbons and lots of hydrogen. So we're going to get a very strong individual signal because all of our hydrogens in this molecule are equivalent. There is effectively 12 of the same hydrogen. So it's ideal for using as a 0. So now we've got a 0 and we want to test our sample. So we need to dissolve our sample in something. However, the solvent needs to serve the opposite function of our reference. We want the solvent to be basically invisible. We do not want it to be NMR active, which is a bit of an issue when we think about most of our common solvents. Take chloromethane, for example. Here we have 3 hydrogens. All of those hydrogens will be NMR active. It's a great solvent, but it's not so great if we don't want it to come up as a signal. And we run into the same problems with most other common solvents. Water, ethanol, all of these contain hydrogens which are NMR active. So what we do is we have to use special deuterated solvents. So here, when we talk about deuterium, we're talking about H2. That is an isotope of hydrogen with 1 neutron and 1 proton. All of the hydrogens are replaced with deuterium, and that makes it NMR inactive, meaning it doesn't give a signal in our proton NMR because its mass number is even. So the H NMR spectra that we get from this is ultimately a plot of electromagnetic radiation frequency versus absorption. The signal in the spectrum is known as a resonance, and the position of these signals is the shift, and that's given in ppm, but don't worry too much about the units. So the proximity to different groups causes different shifts, and this is shown on table 27 of your data booklet. And there are 3 main factors about these groups that are near the hydrogens that affect this shift. That's electronegativity, the aromaticity, that's a benzene ring, and hydrogen bonding. These 3 factors cause increasing shift that's moving to the left away from 0, and you can see that in the table in the data booklet. Groups associated with these factors have larger shifts. So The other piece of information we need to pay attention to is the ratios. And these are given by integration values that are usually on the graph. You either measure these or they're given as numbers. And they tell us the ratio of number of hydrogens in each of those environments. For example, in this case, we have a 2:3:3 ratio. So this tells us that there are 3 hydrogen environments in this molecule. That's 3 different types of hydrogen, and they are at a ratio of 2:3:3. Now I've included the molecule on screen. We can actually see that's the case, a CH3 group, a CH2 group, and a CH3 group. But it may not always be so obvious what a group is and what even is a hydrogen environment anyway. So let's have a look at that. So quite simply, a hydrogen environment is the position that a hydrogen is in. The key being that multiple hydrogens can actually occupy the same environment. So what we're going to do is we're going to follow the 2-bond rule to be able to determine, are these hydrogens in the same environment? Are they different? And how many hydrogen environments are in this molecule? And the 2-bond rule is simple. We're going to follow 2 bonds away from the hydrogen that we're looking at, and we're going to see what is bonded there. We can check that on multiple hydrogens, and if everything is the same, we consider them the same proton or hydrogen environment. Let's take a look at this hydrogen here. I'm going to draw 2 lines and follow 2 bonds and record each. The first one is hydrogen. The other one going straight across is hydrogen, and if I go to the right, I see I'm attached to a CH2 group. Fantastic. That is a hydrogen environment. Now, I'm going to check this hydrogen just to the left of it. I do the same thing again, going 2 bonds down, 2 bonds up, and 2 bonds straight through. Now, these 2 hydrogen environments are exactly the same, a hydrogen, and a CH2. Indeed, I can look at the bottom hydrogen in exactly the same way, and yep, you guessed it, we're going to find that we have hydrogen, and a CH2, meaning that all of these hydrogens are in the same hydrogen environment, which is what we'd expect because they're all bonded to the same carbon on a CH3 group. So we could call this group here one hydrogen environment. Let's have a look at the hydrogens on the next carbon. We follow the 2-bond rule, and both hydrogens show that they have a CH3, a hydrogen, and a CH2 group. So that is one hydrogen environment. So we might quickly say, well, that must mean the CH2 group next to it is also the same. However, if we follow the 2-bond rule with the hydrogens on the carbon next to it, we realize there is an oxygen atom here, and that is different, and therefore the CH2 group nearest the alcohol group is going to be its own separate hydrogen environment. So we could call this first CH2 group CH2A, and that would be its own discrete hydrogen environment. And then if we address the hydrogens on this 3rd carbon along from the left, we see that these 2 hydrogens are equivalent to each other because they both follow the same pattern if we follow the 2-bond rule. So that CH2 group B, if we'd like to call it, is its own hydrogen environment. And there is only one hydrogen in the molecule that we have yet to look at. Now, when a hydrogen is attached to a very electronegative element, like it is to oxygen here, we can consider that hydrogen isolated and not being influenced by the rest of the molecule. So that is its own discrete hydrogen environment. So for propan-1-ol, this molecule, we would expect 4 peaks on the spectrum because we have 4 separate hydrogen environments. So let's get you doing some quick questions before you go and do some more long form questions. First question, what property of hydrogen allows it to be used in NMR spectroscopy? Pause the video. Pop them up. So hopefully you remembered it was the odd mass number that was the key to hydrogen's NMR activity because it has a spin half. Next question then, what is the reference molecule used in H NMR? Pause the video to have a go. Pop 'em up! Indeed, it was the uber-symmetrical tetramethylsilane, or TMS. Silicon in the middle with 4 methyl groups surrounding it. Okay, last one. Turn your hand at finding how many proton environments there are in propanoic acid. Pause the video to give yourself some time. Pop 'em up. Hopefully you utilized your 2-bond rule here to see that there was 3 different proton environments in propanoic acid. And if you'd started using your own shortcuts for that by using groups, that's perfectly fine too. So there are some questions for you to try on this, which is going to be really important before we move on to further structure determination using this technique in the next video. Thanks for joining me again, guys. Don't forget to like, subscribe, and as always, practice makes slightly better.